Good morning, guys. After 10 minutes of technical problems, we can now start. So today I will give a short tutorial on how to run our periodic set thingy. So the set, if for those who doesn't know, it's a self-energy embedding theory solver. So the self-energy embedding is sort of like DMFT-like approximation for the real material simulation. So first of all, to run this code, we need to know what we need to install. And basically, this is all the software we need to have. First, we need to have the Python 3 version to have PySCF and IR basis package. Then we need to have ALP score and 3 packages that depends on ALP score. So basically, it's UGF2, which we use for the weak coupling solution. It's either like GF2 or GW. Then we need to have GFMOL. It's a molecular GF2 GW solver that we use for the double counting solution. Then we need some impurity solver. In this particular case, I show that we need to use. We'll use EDLEAP, which is exact diagonalization solver. And then for the exact diagonalization, we need to have RPAC. And for the rest of the simulation, we need to have IR grid files for the sparse imaginary time grid sampling. So first, let's basically start with building everything starting from ALP score. So first we create directories, and then we load some modules. This is example on the Pauli. On other systems, it will be completely different because other system has completely different compilers and the way how you load them. But for Pauli, you basically can load this one. Then you need to build an ALP score. For that, you clone it from GitHub. You create build directory, go there, call CMake, then basically wait for 20 minutes, then run tests and install it. Then you delete everything in this build directory because you don't need to have all this junk to be lying somewhere around. Then you install RPAC. For that, you also go to the GitHub, you clone it, you go to the same build directory, call CMake, basically ensure that everything works, run tests, and install it, and again clean everything in the build directory because you don't want to have all these object files to be somewhere around because you already installed everything. Then you go to the ED library. So for that, you go on the GitHub, you clone it, you call CMake, make sure that you specify use MPI because otherwise, and also for the RPAC, you also need to specify MPI on, otherwise it will not build the parallel library for the RPAC, and then your EDLEAP will not be able to use MPI, and then you will be screwed in the later steps. So here you specify the CMake flag use MPI, you specify where you have RPAC installed, where you have ALPS installed, and then you specify the path to your EDLEAP source directory, you make it, you install it, and again you clean everything. And then you want to install GFMOL, so for GFMOL you basically do similar. GFMOL depends only on ALP score, so you need only to specify ALP score, then you build it. Then the next step is you need to have UGF2. For UGF2, again, it's simple project that uses ALP score. So all you need to do is basically tell CMake where you want to install it, where the ALP score is installed. Then you build it. You can run tests on it if you have extra half an hour of your life to spend somewhere because this test takes quite a long time to run, especially with recent commits from one of the group members. And then you clean everything because you have everything installed. Then you basically need to build the set. Initially, set code is Python code, but it has some libraries and some executables that you need to have. For example, it has this ED solver that uses sparse grid and uses ED library. Then it has double counting solver that uses GFMOL library, and you basically specify everything as a dependency, and you specify ALP score as a dependency. Then you also need to specify use MPI because otherwise it will not work. then you build it, and out of that you will have 3 executable. You will have exact diagonalization solver, you have GFMOL, and then you also will have integral transformer solver. So then basically the common workflow for the set is basically you need to get integrals and initial solution, for example, a Hartree-Fock or PBE solution. Then you need to get some weak coupling, dynamical solution, for example, GF2 or GW. For that, you need to call the UGF2 solver. Then you need to set up transformation matrices. You need to choose an active space for your impurities, because for the set problem, you can have multiple impurities in your active space, like in comparison to regular DMFT simulation, where you just have like single impurity problem for the whole like embedding procedure. Here you can choose like multiple impurities. You can say, for example, you want to have one impurity for T2G orbitals of your, I don't know, like transition metal, and you want to have like one impurity for your oxygen p orbitals or something like that. So for that you call this set transform.py. Then out of that you will have some HDF5 files with the transformation matrices. Then you use these matrices to transform your Coulomb integrals that you obtained on the very first step to get the Coulomb integrals for your impurity problems. And after you got all this input, you run set by calling this set main.py. So for the first step, you need to set up system, and for that you need basically have some system geometry and atoms that are in your unit cell. So you specify 2 files. One contains basically your lattice vectors, and another contains atoms positions and atom names, and all these numbers are in angstroms. Then you basically call the Python script init data df.py. You tell this script where this like lattice vectors, where the hell is this? Where your atoms with positions. Then you need to specify what basis you want to have for your atoms. So for example, you want to have different bases for lithium and different bases for hydrogen, and you specify individual files for these bases. Also, you can just have single bases for everything in the system. You also can specify pseudopotential by providing these arguments, and then you have 2 outputs in addition to all debug outputs, like the Hartree-Fock solution or PBE solution is in your input.h5, and then you also have 2 sets of Coulomb integrals. One is df_int and another is df_hf_int. The first one does not contain the, it does contain this proper treatment for the divergent term, and the second type, this hf_int, it doesn't have this divergent term in the integrals because it's treated on a separate level on the Hartree-Fock. Then with these 3 like sets of output, you can now run the weak coupling solution. For that you call the UGF2 solver. It has many parameters, probably like about 3 dozens or something like that. But main parameters are here. So you need to basically tell how many electrons you have in your unit cell, how many orbitals you have in a unit cell. Then you need to tell this the solver how many K points you have. And if you use the irreducible grid, you also need to tell how many irreducible K points you have. Then you can choose the number of spin you have. If it's 1, it's apparently the spin restricted solution. If it's 2, it's a spin unrestricted solution. Then there is NQ, which is the number of auxiliary basis function in your Coulomb integrals. So we store Coulomb integrals in the 3-index tensor, and basically first two indices is your orbital indices, and last index is your this auxiliary basis function. Then you need to specify how many tau points you have by providing the dimension of your sparse basis grid. Then, of course, your temperature, number of iteration, type of the self-consistency. This will be changed in the next release. So right now it's an integer parameter, so it's either 1 or 2. So 1 is for the GW, and 2 I think it's for GF2. Then you need to also provide these 3 parameters. This parameter, it tells you whether you want to have IR basis or you want to have Chebyshev basis. By default, it's Chebyshev basis. Then you need to provide the path for 2 files. It should be the same file, otherwise it will not work. I don't know why there is 2 parameters for that, but yeah. So, and this is basically file where you have this sparse grid either in Chebyshev basis or in IR basis. And then you run your GF2 solver by providing all these parameters, and your output by default is sim.h5. You also can change it and name it whatever you want. Then after you get this input, you want to basically prepare your set input. For that, first you need to call set transform to create the transformation matrices to project the whole system onto local projected impurity problems. There is 5 input parameters and 1 output parameter. So the input parameter, you tell whether you want your whole system to be orthogonalized, and if you want to say what type of orthogonalization method you want to have. So it's either symmetrical or canonical orthogonalization. Then you want to choose what is your impurities. By that, you provide multiple active space parameters, and here you list the orbitals in your unit cell that gonna be your impurity orbitals. And here, for example, I have like 2 impurities. Both impurities has 2 orbitals. First impurity is 0, 1, and second impurity is 2, 3. And then also the last parameter here is like input parameter, tells basically whether the input that we have for the set transform is in the irreducible K-grid or it's not in just like in regular grid. And the output parameter is basically the H5, like name of the H5 file, which will have all these transformation matrices inside it. Then when we get this file, we can now prepare the Coulomb integrals by calling intransform, C++ code. It has 3 input parameters. First, it's your transformation matrices, then the path to the Coulomb integrals. So we should use this df_int because otherwise our local integrals will not be more or less correct. Then this parameter is for the large systems. If you set it to 1, it will by default create intermediate transformation matrices, and it will always do this. And then you call basically like the data to, like you call, when you call it, your output will be written in this H5 file. But sometimes it takes too long to run, and you can, for example, get this intermediate transformation matrices, but then your run crashed and you have these files and you don't want to spend this time again, so you put this to 0 and it will just reuse the previous transformation, like transformed matrices to create the local Coulomb integrals into this H5 file. So after that, so we have everything in place. So we have Hartree-Fock solution and Coulomb integrals from PySCF in these 3 inputs. Then we have weak coupling solution in the sim.h5. Then we have transformation matrices, we have Coulomb integrals, and then we need to choose what type of impurity solver we want. So here, for example, for the ED, you also need to specify some parameters for the ED solver. For example, you need to have the ED parameter file. You need to have bath file which contains initial guess for your bath, because when you do fitting, you want to have basically some initial guess that is close to the real solution. Otherwise, you will obtain some nonsense. Then there is a min types file which contains type of minimization, because for different type of hybridization function, different type of minimization works better. And that's why you always need to check what is your output, how your delta, how your hybridization function looks like. If it's metallic, you want, like, if it looks more metallic, you will have like one type of minimization. If it looks more insulating, you will have another type of minimization. Then skip this, and then basically we can run set with, like, this is like a minimum parameters you need to have. So you want to have orthogonalized data. Your data come from irreducible Brillouin zone. Then there is like all type of inputs. You specify your temperature, you specify type of your impurity solver, you tell how many impurities you have. Here, for example, I have 2, and for impurity solver, I have this class for the ED solver. Then we need to specify the double counting command. Here I call this gfmolset executable, and then to also have exact diagonalization command that we want to run, because we choose impurity solver to be ED solver. If you choose different one, these like last 4 parameters will be different. And then you run and you obtain some results, and after that you do all the fancy post-processing. And I think that's it for today.